Okay, I hope I'm audible to all students who are attending this particular practice lecture for mathematical methods for economics. In this particular practice lecture, I'm going to solve a few numerical problems based on the concept of partial derivatives. Recall that in the previous lecture as well, we had done some good practice of solving and calculating partial derivatives given a function in several variables. So in this particular lecture as well, we are going to solve a few more problems based on the concept of partial derivatives. So let's quickly start with this particular lecture. I'm just writing the main heading for completeness. We are looking at practice problems. We continue with our discussion of some practice problems based on functions in several variables. If all students can recall that in the previous lecture, we had solved a few problems on partial derivatives. Let's quickly continue with that. Let's look at question number 1 for this particular lecture. Let the function z be equal to a function of x square minus y square. The question is asking us to show that y times del z by del x is equal to minus x times del z by del y. So we are given the function and we need to show this particular result. So let's quickly start with the left hand side. The left hand side is y times del z over del x. So what is del z by del x? So let's quickly calculate this. Del z by del x will be the partial derivative of the function with respect to z. Remember, when you are partially differentiating with respect to z, you treat x. When you are partially differentiating with respect to x, you treat y as a constant. So the derivative of this will be, it's a composite function, so it's going to be f dash x square minus y square times the derivative of x square minus y square partially with respect to x is just 2x. So I get 2x times f dash x square minus y square. This is my del z by del x. So my left hand side, if I write it again, it's going to be y times del z by del x. Del z by del x is 2x f dash x square minus y square. If I calculate this further, I get 2xy f dash x square minus y square. Mark this as result 1. Now let's consider the right hand side. The right hand side is minus x times del z over del y. Now let's calculate del z by del y. When you are finding del z by del y, that means you are partially differentiating the z function with respect to y, treating the variable x as a constant now. So when I partially differentiate the z function, again, it's a composite function. So first I have f dash x square minus y square times the derivative of x square minus y square partially with respect to y is minus 2y. So I get minus 2y f dash x square minus y square. So I've got del z by del y. Therefore, minus x times del z by del y will be what? Because ultimately I need to calculate the right hand side. So minus x times del z by del y will be minus x times del z by del y is minus 2y f dash x square minus y square. So this minus and this minus makes it plus 2xy f dash x square minus y square. This is equation result 2. If you compare, left hand side is this expression, right hand side is this expression, both are the same. Clearly, left hand side is equal to right hand side, hence verified. Hence verified. So I have shown that y times del z by del x is equal to minus x times del z by del y. So I hope all students attending this lecture have understood this particular question. Then let's look at the next set of questions. Now remember, from my lectures on partial derivatives, we have also talked about linear approximation for partial derivatives, and we have also looked at the equation of a tangent plane. Okay, so let's quickly do a practice problem based on the linear approximation which we have covered, or the equation of the tangent plane. So first of all, I'm just quickly revising the theory. Recall from my lectures on functions and several variables. Recall from my theoretical lectures on functions in several variables that the equation of a tangent plane, to the function z, which is equal to a function of x and y at the point x0, y0, z0 is given by, remember the formula from the lectures? It's z minus z0 is equal to del z by del x times x minus x0 plus del z by del y. So these partial derivatives are evaluated at x0, y0, z0. Similarly, del z by del y evaluated at the point x0, y0, z0 times y minus y. So this was the equation of the tangent plane, which I had covered clearly in my lectures on functions in several dimensions. Now, based on this particular concept, let's look at a practice question. So find the equation of the tangent plane. Find the equation of the tangent plane to the function. Find the equation of the tangent plane to the function z is equal to x minus y over x plus y, where x and y both are equal to 1. Or I can say they are approximately equal. They are equal to 1 approximately. That means we are given that the points are x0 is 1, y0 is 1. If I put these points, can I calculate z0? So z0 will be, so from here z0 will be x0 minus y0 over x0 plus y0. x0 is 1, y0 is 1. So if I plug in the values, I get z0 as 0. Okay, if I quickly calculate del z by del x, that's the partial derivative of the z function with respect to x. Its denominator into the derivative of the numerator is 1 minus numerator into the derivative of the denominator is again 1 with respect to x partially over denominator square. This is the famous question rule. Okay, if I solve the numerator, I get x plus y minus x plus y over x plus y square. X and minus x cancel, I get 2y over x plus y square. And if I now evaluate del z by del x, particularly at the point 1, 1, 0, because x0 is 1, y0 is 1, z0 is 0. So evaluating it at the point 1, 1, 0. So I can write here my points x0, y0, z0 are 1, 1, 0. So if I put the values here, so 2 into y0 is 1 over x0 plus y0 square. So 1 plus 1 square. This is 2 over 2 square, which is 2 over 4, which is half. So del z by del x has come out as half at the point 1, 1, 0. Let's calculate del z by del y. So if I quickly do that, so if I erase, so I am writing it here just for clarity that del z by del x has come out as half at the required point 1, 1, 0. Now I'm erasing this portion off and I'm calculating del z by del y. Erasing this part off. For del z by del y also, guys, we use the question rule. So its denominator into the derivative of the numerator is minus 1 with respect to y partially, minus numerator into the derivative of the denominator is 1 with respect to y partially over x plus y square. So this is minus x minus y minus x plus y over x plus y square. minus y and plus y cancel out. I get minus 2x over x plus y square. If I evaluate this expression, particularly at the point 1, 1, 0. So minus 2 times x is 1. X is 1 and y is also 1. So I get minus 2 over 1 plus 1 is 2. 2 square is 4. I get minus half. So I get del z by del y as minus half at the point x0, at the point 1, 1, 0. So these are the values I've got. Now just plug them in this particular formula to get the required. Okay, so let's plug them in this particular formula. So if I erase this particular portion of, erasing this part of, let's quickly evaluate the above expression. So I can write that the equation of the tangent plane is equation of the tangent plane is z minus z0. How much is z0? 0 is equal to my del z by del x has come out as half times x minus x0 is 1. Del z by del y has come out as minus half times y minus y0 is 1. So I get z as half times x minus 1 minus half times y minus 1. So I get this implies z is equal to x minus 1 minus y minus 1 over 2. So I get z as x minus 1 minus y plus 1 by 2. Minus 1 and plus 1 cancel out. The equation of the tangent plane and the final answer for this question is z is equal to x minus y over 2. This is the equation of the tangent. So I hope all students attending this lecture have understood how we have solved for this particular problem. Okay, so now let's quickly move forward. The next set of concepts we have done in our lectures on functions in several variables was the concept of partial elasticities. Okay, if students can see my lectures on partial elasticities, you will see that we have done that particular concept in quite depth. Okay, so I'm just quickly revising this with all students. So just as a revision, let's quickly go over it. Students can write the heading economic applications of partial derivatives. Economic applications of partial derivatives. And one of the major economic applications is calculating partial elasticity. So students can write the heading partial elasticity of demand. Partial elasticity of demand. I'm just quickly revising it. We have already done this in our theoretical lectures, but still, just as a revision, let P1, P2 denote the prices of two commodities, capital X1 and capital X2, and small x1, small x2 denote the quantities demanded, of the two commodities, capital X1 and capital X2. So I can write, therefore, we can represent the demand functions as, so if I use a functional notation to denote the demand functions, I can write that demand for commodity 1 is a function of prices P1 and P2. Okay, and demand for commodity 2 is also some function G, another function G of the prices P1 and P2. This is how I can write the demand function. Okay, so if I calculate first point, if I calculate the direct partial elasticity. So direct partial elasticity. How do I calculate the direct partial elasticity? So I can say that eta I, or I can say in general, eta 11 is the partial elasticity, of commodity X1 with respect to price P1, which I can also write as minus P1 by X1 times del X1 by del P. Okay, and similarly, eta 22 is the partial elasticity of commodity X2 with respect to its own price P2, which I can write as minus P2 by X2 times del X2 by del P2. So eta 11 is the direct partial elasticity of commodity X1 with respect to its own price P1. Eta 22 is the direct partial elasticity of commodity X2 with respect to its own price P2. Okay, where all of us know that partial elasticities are going to measure the degree of responsiveness of the change in quantity demand with respect to the change in price of that commodity, keeping all other factors constant. We know the definitions of elasticity from the microeconomics course. Okay, and similarly, we can also look at the cross partial elasticities. So if I erase this particular portion of, after having looked at the directs, I am erasing this part of, let's also look at the cross partial elasticity. So all students attending this lecture can write the second point, cross partial elasticity. Cross partial elasticity. So I can write that eta 12 denotes the partial elasticity of the demand for X1. It denotes the partial elasticity of demand for commodity X1 with respect to price P2. And the formula for this is P2 by X1 times del X1 by del P. And similarly, eta 21 denotes the partial elasticity. It denotes the partial elasticity of demand for commodity X2 with respect to price P1. So I can write that therefore eta 21 is P1 by X2 times del X2 by del P. So these are now the cross partial elasticities. These are going to capture the demand for one commodity when the price of the other commodity changes. Okay, I can also write it in log terms. I can also write this as del log X1 over del log P2. And this in logarithm terms, I can also write it as the partial derivative of log of X2 with respect to the partial derivative of log of P1. Del log X2 by del log. These are alternative formulas which involve logarithms. Okay, and now erasing the initial part of, I can also write a note which allows us to check whether the commodities are substitutes or they are complements. Something we have learned in our demand theory lecture. If I erase the initial part off, I can write a note that if eta 1, 2 and eta 2, 1 are both positive, it implies that the two commodities x1 and x2 are substitutes. Why? Because if the cross partial elasticities are positive, it means I'm saying that an increase in the price of commodity 2 is increasing the demand for commodity 1. This happens only when the two goods are substitutes. Suppose tea and coffee we all know tea and coffee are substitutes. When price of coffee goes up, demand for tea will go up. So we would expect the cross price elasticity to have a positive sign in case of substitutes. This was point 1. Point 2. If the cross price elasticities eta 1, 2 and eta 2, 1 are both negative, if they are both negative, it implies that the two commodities x1 and x2 are complements. They are complements. Like tea and sugar. When price of sugar goes up, demand for tea will go down. That means for complements, we would expect the sign of cross partial elasticities to be negative. So I hope students have understood this. And now let's look at a practice problem based on this particular concept. So if I erase all this off, let's look at a practice question based on this particular concept. Consider the following demand functions. Consider the following demand functions for two commodities x1 and x2 given by, we are given that x1 is equal to p1 to the power negative 1.7, p2 to the power 0.8, and we are given that x2 is p1 to the power 0.5, p2 to the power negative 0. We are given these two demand functions. The question asks us to find out eta 11, eta 12, eta 21, and eta 22, and determine whether the two commodities are substitutes or complements. Determine whether the two commodities are substitutes or complements. Okay, so let's quickly solve for this particular problem. Okay, so let's find out first of all eta 11. It is eta 11 will be p1 by x1 times del x1 by del p1 with a negative sign because of law of demand all elasticities are negative, price elasticities are negative. So if I find out del x1 by del p1, if I partially differentiate this demand function with respect to p1, I get negative 1.7 times p1 to the power negative 1.7 minus 1, p2 to the power 0.8. So this is negative 1.7, p1 to the power negative 2.7, p2 to the power 0.8. Okay, so this is my del x1 by del p1. So my eta 11 will be minus p1 over, put the value of x1 from here. x1 is p1 to the power negative 1.7, p2 to the power 0.8. Del x1 by del p1 is negative 1.7, p1 to the power negative 2.7, p2 to the power 0.8. This cancels, minus minus make it plus. So I get 1.7. P1 and P1 to the power minus 2.7 makes it P1 to the power minus 1.7 over P1 to the power minus 1.7. This also cancels out. My answer is 1.7. So I can write here that eta 11 has come out as 1.7. Let's calculate eta 22. That is minus P2 by x2 times del x2 by del P. Now, what is del x2 by del P2? Partially differentiate the demand for good x2 with respect to price P2. So I get negative 0.2, P1 to the power 0.5, P2 to the power negative 0.2 minus 1, which makes it negative 1. Okay, so this is del x2 by del P2. Therefore, eta 22 will be minus P2 over x2 is what? P1 to the power 0.5, P2 to the power negative 0.2 times del x2 by del P2 is minus 0.2, P1 to the power 0.5, P2 to the power negative 1. This cancels, minus minus makes it plus. P2 multiplied by P2 to the power. So first of all, I have a 0.2. Let me write that. And then P2 multiplied by P2 to the power negative 1.2 makes it P2 to the power negative 0.2 over P2 to the power negative 0.2. This cancels out, I get 0. So on the top, I can write that eta 22 has come out as 0. And now let's calculate eta 12 and eta 21, the cross partial elasticity. So I erase all this off. Erasing all this off. Let us look at how we calculate eta 12. This is P2 by x1 times del x1 by del P. Let's calculate del x1 by del P2 first. It's the partial derivative of x1 with respect to P2. So it's 0.8, P1 to the power negative 1.7, P2 to the power 0.8 minus 1, which is 0.8, P1 to the power negative 1.7, P2 to the power negative 0. So this is going to be P2 over x1 is how much? P1 to the power negative 1.7, P2 to the power 0.8 times del x1 by del P2 is 0.8, P1 to the power negative 1.7, P2 to the power negative 0.2. Now this and this cancel out. I get 0.8, P2 to the power, this multiplied by this is P2 to the power 0.8 over P2 to the power 0.8, which is my denominator. Things get cancelled out. Answer is 0.8. That means my eta 12, therefore eta 12 is 0.8. Eta 21 will be P1 by x2 times del x2 by del P. Now what is del x2 by del P1? Partially differentiate x2 with respect to P1. I get 0.5, P1 to the power 0.5 minus 1, P2 to the power negative 0. This is 0.5, P1 to the power 0.5 minus 1 is minus 0.5, P2 to the power negative 0.2. Put everything in the formula. So eta 21 will be P1 over x2 is P1 to the power 0.5, P2 to the power negative 0.2 times del x2 by del P1 is 0.5, P1 to the power negative 0.5, P2 to the power negative 0. This cancels with this. I get 0.5. P1 times P1 to the power negative 0.5 is P1 to the power 0.5. Denominator is P1 to the power 0.5. This and this cancel, I get 0.5. So I get my eta 21 as 0.5. Now this is also greater than 0. This is also greater than 0. So I can write, since my cross partial elasticities are both greater than 0, therefore x1 and x2 are substitutes. Goods x1 and x2 are substitutes because we have just done a few minutes back that if the cross partial elasticities are positive, both the goods are substitutes. So I stop in this particular lecture. The objective of this lecture was to look at some more practice problems based on functions in several variables. In the next lecture, in the next practice lecture, we are going to look at more practice problems on partial elasticities. So I stop in this lecture. I hope all students have enjoyed this lecture. Okay. Any doubts, you can unmute your mic and ask, or you can get in touch with me for doubts on call or WhatsApp, or you can mail me all your doubts at divineschoolofelconomics@gmail.com. This is where I stop in this particular lecture.